in Francisco and NVIDIA. So our goal is to build not just a digital twins, right, of the grid system, but also a language model that work on top of that digital twins. So our grand plans, right, if we have infinite money and infinite people, infinite GPU, our goal is to actually build like a virtual worker that can operate grids a lot more effectively. And the problem is like with the rise of data center and so on, the energy demands become extremely hard to manage. And given all the climate change and so on, all the hurricane and so on, especially in Florida, is getting more extreme and extreme. And grid also become bigger and bigger, especially in the US. So us as a human, right, we could not always operate fast enough in this like over changing area. So what if we can build a worker that can give us recommendation, so we still there to make the final recommendation, but there's a group of virtual workers that can go in and then do all the analysis, like uncertainty quantification, what would be the best path forward if one of the transformer like go down and so on. That would be ideal case, right? So we can just like look at the top 5 recommendation, pick one that we like, and then we operate in according to that recommendation and so on. But the main problem is this language model, right? Like GPT, Claude, Gemini, whatever. Even though it's extremely good in language, it doesn't really have physical knowledge. So nowadays there's a two big words, I guess, world model and neural symbolic. They're all like kind of big words, but technically you want to be able to make sure that your neural or language model actually give you output that actually physically grounded, or the symbolic part, or the deterministic part of the word. But you don't want your language model, right, to go out and actually operate the real grid, and then trial and errors on that real grid, on that real transformer, or that real like power line, because that would be extremely harmful, right? It will make a lot of mistake before it finally makes something useful. So our goal is to like train those agent or language model within this copy of the physical world, so that it can like keep learning, million hours upon million hours in this digital system without create any real world damage. But I think how we create this world model is still very different, like according to different people. But if you look at this Yalakun and big people in the communities, right, they were like can learn from video and so on. And but I think we take a different approach. We're thinking of this world model as like a multi-scale problem. So you can think of grid, energy grid, right? Start from like an equipment level, like transformer, switchgear, gas turbine, power line, and so on. And then all of them stick together, right, into a substation level, and then many substation combine turn into a city, and many city would turn into a grid, like a East Coast grid, West Coast grid, Texas grid, and so on. But how to build this world model is a huge question right now. And I want to start with like, is the data actually abundant, right? Like in language model, people would say like, yeah, we can just grab the internet, all the book that written in this whole world, all the like Stack Overflow, Reddit, uh, Facebook posts, and so on. So in language, well, it seems to be abundant, right? It's like everywhere. We've been creating text in the invention of language anyway. And to make analogy to the language model, right? And this may not be the most up to date at this point. I think this presentation made um couple 6 months ago, I think, that this slide. So you can see that's like the number of token is like trillion, right? Not just billion. So when we think of physical world, do we actually have these kind of data to train just one model? And in back to in physical world, right? We don't have internet to go on and scrap it. So what we could do is like we have to find sources like real measurement, from SCADA, from AMI, from drone, nowadays to like go onto the remote area in Pennsylvania or in Florida, let's say, and then take photo of those equipment. And those would be one source of data. But the second source of data would be a simulated one. So you could, have your physical base solver. It can be like ODE, SDE, PDE solver that or particle base, if you like, that you develop in the past like 50 years, and then you can produce data from this, and this would be less noise, right, in a more controllable way, but also it's also full of assumption and might not always reflect the real world that you see in the measurement. And let's talk about the measurement first. So this is a Siemens gas insulated switchgear, one of the bread and butter that Siemens sell stuff. And you can see this gas insulated switchgear, like you interest in the thermal sense of it, right? So it's actually a conjugate heat transfer problem, but the quality the quantity that you're typically interested in is a temperature field, because you want to make sure that the temperature is less than certain threshold, so it's not break technically. And if you look at these gas insulated switchgear, right, you you might have like one or five sensor top to measure the temperature, which is actually pretty sparse. So it's fragmented, right? Like you cannot actually see the temperature distribution like what you could get from numerical solver, but it's real. So the measurement is typically real, but it's very sparse, very costly. Like these five sensor, Siemens need to pay a lot of money to get it there, and so on. It's also very noisy. So even though it's real, it's come with a lot of problem of itself. So what about people might argue, right? We know, system of equation that simulate all these, and then we could like, yeah, why not just simulate everything that is there, and then we can, grab all the stuff from this simulation. So this what you see is like a very small part of a transformer. It's just like a part of the actual transformer that one want to simulate, and it's like where the fluid kind of flow through this, and it's governed by a classical CHT, right? You have a fluid region which is governed by Navier-Stokes with Busnick approximation. You have a solid region that's technically heat conduction, and then you couple them together with the interface between fluid and solid. But because the wall between fluid and solid is like everywhere, and it's like you have a very thin layer between solid and fluid phase, and typically, right, your time step will be governed by, first of all, if you solve implicit or explicit. But let's say you don't have stability problem, it's still governed by your CFL condition, right? If you don't want to overstep, otherwise you not get the accurate answer. So with a very thin mesh and pretty high velocity, you have a very, very small time step. So this is like a joke that I used to make to the to the leadership team here. It would take 16 days to to simulate this system on the 75 minutes of physical time. So technically you could just run transformer for 75 minutes and you get the answer before the actual simulation finish. And that's kind of funny. So, and I think this is actually the topic of today's talk. So we, people might argue, right, that like you have physics informed neural network, you have those like physics informed neural operators. I think if you talk to Hong Q, he would say the same. That's like it's extremely hard to train those models. So at the end of the day, at least in my knowledge, it still have to be a hybrid between both, right? You still need to generate some data. At least you need to validate your model. And then you can integrate, your physics inform to your machine learning model, and then you use them together. So our thought here is like, okay, let's start with, if we don't want to wait for 16 days, if we want to generate some data, at least to validate, our machine learning model faster, could we do it? And there's a lot of like movement, right, to implement your solver from CPU to GPU to leverage this new type of machinery so that we can get the result faster and faster. And I would say this is nothing new, right? Our ideas actually come from typical multi-grid recycle system. So, long story short, if you have like a sawtooth multi-grid, right, you technically have just like cost to phi. That's what Chris group from Imperial College doing. So we working with them to do a recycle, which means you do from phi to cost, transfer the errors, and then cost back to phi the correction path. So technically it's a prediction correction type of framework. And then if you look at the second part of the slide, right, you see that you can actually do this coarsening and refining into a graph representation. So if you look at this, you can think of it as a, in machine learning, people will just think of it as a unit right away. So any phi to cosify unit representation. So it fit very well with what people already did in the machine learning world. So we kind of combine what people did in the classical numerical method into what people did in the machine learning world. So technically it's a graph multi-grid on GPU system. And our framework is, also try to make it more like open source, right? So we build it, based on our open source framework. So we get a geometry. It can be from any CAD model and so on. And then we want to create a body fit mesh. So we don't do any cut mesh or any like embedded mesh at this point in time. It's all body fit mesh. And then we rely on Gmesh with also a open source model. And then we want to discretize it, right? To find the function space before we move on to the GPU side of things. So we use Phoenix X or Dolphin X to be precise as a backend to to get these metrics out of this discretization system. And then we move all of these metrics from CPU to GPU and then perform the graph multigrid as a preconditioner. And then we use typical conjugate gradient as a solver. And it can be, steady state. Let's say we use simple algorithm for steady state, or you can do Runge-Kutta in the or implicit, explicit actually in the transient type of thing. And it show here 1 to 8 GPU. That's a paper level, a paper version. I think we tested up to 128 GPU at this point, and the weak scaling and the strong scaling is pretty decent, I would say. So yeah, but just want to say, like, let's say and we show here 1 to 8, right? Because in the current setting, each node have 8 GPUs. So we only test in this paper like within one node. But when you go across node, 128 GPU, now the communication like become a little bit more bottleneck, but it still provide you a certain good scaling law here. And we want to say we build on top of what Imperial College is doing, right? So they call it a neural physics framework, technically based on Cartesian grid. So in machine learning, you will think of it as a convolutional neural network, right? But the main problem of that solver that we could not use it out of the box is that our mesh is very complicated. We try to do like cut mesh, embedded mesh on the Cartesian grid. It just not work very well. That's why we move on to the unstructured mesh type of thing. And these figures just try to like map 1 to 1, right? To show that like what we change from their starting point and develop into our own like body fit finite element based GPU solver and so on. I think that the three main key here that's one might need to think about is that it works on unstructured mesh. It's a PyTorch based native. It doesn't use any like warp from NVIDIA or AMGX or whatever. So it's built everything on PyTorch, not JAX either. And it can work from 1 to 128 GPU. So we can go up to like 10 of billion degree of freedom at this point to solve one problem. And yeah, I think all sounds great, right? And I think we're about to put the paper on archive. But anyway, like a teaser at this point. So we solve it on 4 different benchmark. And this is like a cavity flow. Typically, we have a 2D and 3D. And then what we try to show here is like we compare against 4 different type of solver. The first one is OpenFOAM 12. The second one is Phoenix native on CPU. The third one is the CNN based from Imperial College, and our proposed GNN based solver here. So yeah, OpenFOAM is still a gold standard, right? In this kind of thing. So in like a smaller problem, the CPU base still like hard to beat, I would say. But when it's getting bigger and bigger and bigger, our GPU base can reach up to like 25 times of the OF12 or like 310 times ahead of the Phoenix X on the on the CPU base. And yeah, some of the case not even converge because it's just take too long time and we don't really have money to spend a lot on the compute time to wait until it converges at this point. But yeah, all in all, like this framework will getting more and more attractive, I would say, when you deal with bigger and bigger problem. So if you have a small problem, you don't really need it. You can just go with the traditional like CPU path. And yeah, people talk a lot about like scaling law, right? If it's actually scale on different GPU. I would say yes, if you have the correct algorithm to make it scale. So if you like do a native block Jacobi, right, that would not scale at all. It's actually getting worse and worse. But if you do, let's say not just two level cost correction, right? There are other methods too. But if you pick the right algorithm to use, it will give you some sort of strong scaling here, at least. And I think one thing that people will not think a lot is that when you do everything in either Torch or Jax, right? This framework being developed for, you know, machine learning model, which require forward and backward pass, which mean all the implicit gradient is embedded in those framework. And if we think about subsurface too, right, or any engineering problem, we want to do, UQ, inverse modeling, topology optimization, and whatnot. And those typically would require you to have an adjoint system, and then you solve KKT, right? And that's actually a huge task in, optimal control problem. But if you migrate your framework into this new paradigm, you actually get all the implicit gradient as a byproduct. And what we try to show here is that we just want to show that at first it's correct. We compare it with the finite difference gradient is correct. But also when the number of parameter grows, right? We only show 1 to 32. But if you think of subsurface that you have, every point in your reservoir is uncertainties, right? Or parameters. You could go up to like million parameters here. And if you go with the traditional route of the central difference and the adjoint based system, your cost actually keep going. It's linearly scale with your scale of the problem. But with the implicit gradient, it's actually constant cost. So at first it will be more expensive, right? But only at the 3 parameters of the break even. So I would say in the if it's not in the control setting, you definitely have more than 3 parameters here. So I would say this is something that you might also want to think about. It's not only you get a faster solver, right? You also get a much faster optimal control framework. Yeah. And yeah, thank you for taking the time to to listen to what I rambling today. And I think there's just 2 points that I want to make here. It's like people talk a lot about foundational model, like including all our collaborators, like Yongsu. We've been talking a lot about this, and I still think at this point that there's no like way of getting from this like gel of zero data at all. It just had to come from somewhere. It's either you generate it by physical solver or you measure it. They all have its own cost, right? But you still need some of them, even though you have physics informed type of framework. So at the end, you just need to be able to generate your data faster. If not, yeah, there's just no point of doing that. And then what not only GPU, right? There's a lot of push nowadays to create new type of hardware too. If you look at the startup world, it's like all the new silicon companies raise like billion upon billion of dollars because I think software is going a lot faster than hardware at this point. So I think that would be a catch up from the hardware side of thing to, unlock more potential in this kind of world. So yeah, those are two things. Thank you very much. If you have any question, let me know.